Solow Growth Model for UGC NET examination. Let us first discuss how the Solow Growth Model came into being. It came after the Harrod-Domar Growth Model. The limitations of Harrod-Domar model prompted many economists to think further in the realm of growth theory. So, what happened in the Harrod-Domar model? In Harrod-Domar model, we had the growth rate given by G is equal to S by V, where S is the savings rate over time ds dt, V is the capital output ratio or the incremental capital output ratio. We can write it as this or this, dk dy. So, this and this are same and V can represent any one of these. According to Harrod-Domar model, S and V are constants. Therefore, G is also a constant. Now, in Harrod-Domar model, we had two types of growth rate, the actual growth rate and the warranted growth rate. Now, the warranted growth rate is the growth rate that entrepreneurs will be satisfied with or capital owners will be satisfied with, and the actual growth rate is what happens in reality. If GA is equal to GW, then economy, if GA is equal to GW, then economy grows. Economy is perfectly balanced and demand and supply balance each other. Now, if GA is greater than GW, then unsustainable boom happens, that is, demand grows faster than businesses can replenish their capital stock. Therefore, as demand grows faster, the prices of goods keep on increasing, but the businesses are unable to meet up with the demand under this condition, because of which there is a uncontrollable boom in the economy. Boom. Now, another thing that might happen is GA can be less than GW. Now, here what happens is recession. This happens because the actual growth rate is less than the warranted growth rate. Therefore, demand falls and prices also fall. Excess capital stock in the hands of the businesses, and this leads to a recession. Therefore, GA is equal to GW is the only condition under which an economy can grow smoothly. Therefore, this is also called a knife edge condition. But in reality, we often see that this is not the case. And policymakers do have a certain leeway while selecting policies. So, in order to make Harrod-Domar model more realistic, economist Robert M. Solow developed the Neoclassical model of economic growth in 1957. Now this is very important for your UGC NET exam. Remember that Robert Solow developed the neoclassical model of economic growth in 1957 and he was awarded the Nobel Prize in Economics in 1987. Now, Solow extended the Harrod-Domer model by adding labor as a factor of production and assuming that the capital output ratio is not constant. So the capital output ratio is the V, which is the G is equal to S by V for Harrod-Domer model. In Solow, that V is not assumed to be constant, unlike Harrod-Domer model. Now, let us start with how the Harrod-Domer model is designed. The production function in Harrod-Domer model is given by y is equal to E into a function f of k comma L. Here k is the capital, L is the labor, f is the production function which uses capital and labor as input, and y is the output that is produced via this production function, and E is the level of technology. Now, so suppose if E increases, then this y will increase. So basically, higher the level of technology, higher will be our output from a given set of inputs. Now, in Solow model, we often assume the Cobb-Douglas production function, which is given by f k L. This will become k to the power alpha L to the power beta, and beta is equal to 1 minus alpha. This is the Cobb-Douglas production function. So we can write it down here. So y becomes E into k to the power alpha into L to the power beta. Now this will become, now when we differentiate it, therefore this will become dy equal to, so we will use chain rule. So basically we will first differentiate this keeping this and this constant, then this keeping this and this constant, then this L keeping this and this constant, and all will be summed with each other. So differentiating this, we get dy is equal to dE into k to the power alpha into L to the power beta plus alpha k to the power alpha minus 1 L to the power beta into E plus beta L to the power beta minus 1 into dk beta L to the into dl into k to the power alpha into E. Now we have dy is equal to, now we know that fkl is equal to this we know, therefore substituting this here we will get dE into y by E, because this becomes this and this multiplied by E is y, therefore y divided by E is this, plus this will become, we will multiply this by k and then divide it by k, therefore we will get dk by k into, so multiplying k, we divided by k, so we will multiply by another k, and this will become alpha into k to the power alpha into L to the power beta into E. Now we know that this term becomes y. Similarly, we will multiply and divide by L the last term, and this becomes dL by L into beta into same thing, k to the power alpha into L to the power beta into E. Therefore, finally we will get dy equal to dE dE by E into Y plus dk by k into y into alpha plus dl by l into y into beta. Now we will take dy, we will take y common from the right hand side and bring it down to the below the left hand side. This will give us dy by y is equal to dE by E plus dk by k into alpha plus dl by l into beta. This is our growth accounting equation for the Solow growth model. Alpha is the elasticity of output, that is y, with respect to capital, that is k, and beta is the elasticity of output with respect to labor, dE by, with respect to labor. This is our, so they have used delta, I have used small d, but it means the same thing. This is change in y basically. So we have rate of growth of output equal to rate of productivity growth, technology growth basically, plus alpha k, which is elasticity of output with respect to capital, multiplied by rate of capital input growth, plus elasticity of output with respect to labor, multiplied by rate of labor input growth. This equation is called the growth accounting equation. Growth accounting provides useful information about sources of growth. It, however, does not completely explain a country's growth performance. Because growth accounting takes the economy's rates of input growth as given, it cannot explain why capital and labor grow at the rates they do. The growth of capital stock is the result of saving and investment decision taken by households and firms, while the growth of labor depends on population growth. By taking capital stock and labor as given, growth accounting presents a static picture. In the next section, we will we'll take a closer look at the dynamics of economic growth. Now, this part will be very important for all of you who are preparing for the UGC NET exam, which is the assumptions of the Solow growth model. The main assumptions of the Solow model are as follows. The economy operates under full employment of inputs. There is no government interference, so this is one. So there is full employment. There is no government interference in functioning of the economy. It is a free market economy. There is no external trade, so it's a closed economy. The economy operates under a neoclassical production function. So as we said, we showed you one of the examples of a neoclassical production function, which is the Cobb-Douglas production function. It can be many other things, but it has to exhibit constant returns to scale. So what is constant returns to scale? So there can be three things: constant returns to scale, increasing returns to scale, and decreasing returns to scale. So say your function is like y is equal to f of k comma l. Now you increase each input by a unit of z. So say you make f k comma l, you make it f of z into k comma z into l. Now when you increase both units by z times, constant returns to scale tells us that it should increase the output by z times as well. See, that is what constant, if all factors of production are doubled, output will be exactly doubled. So for any positive number z. Both capital and labor are essential for the production. Now we will, so these are 4 assumptions. Now we will go into assumptions on the production function. Now since we already know that the capital that this is a constant returns to scale, therefore we can reduce the number of variables by dividing the capital by labor and using only per unit capital per unit labor as our variable. This will make computations much simpler. Therefore what we do is we divide k by l and l by l, therefore we get y by l equal to f of k by l comma 1. Therefore this is, we represent this by small y, we represent this by small k, therefore we get y is equal to f of k. This is what we get. Basically this we get y is equal to f of k comma 1, which can be reformulated as y is equal to f of k. Now this has to satisfy certain conditions for it to be acceptable as a production function in the Solow growth model. The main assumptions are f dash k has to be greater than 0, that is the first derivative of f has to be greater than 0, therefore f is increasing, and the second derivative has to be less than 0, therefore the rate of increase of f is decreasing, right. So the first derivative is positive, second derivative is negative, and also f0 has to be 0. So if there is no input, there will be no output. So this is how the fk function looks. It is increasing but at a decreasing rate. So this is output per worker and this is capital per worker. So it is increasing at a decreasing rate. So this has the diminishing marginal productivity of labor. So marginal productivity of labor is marginal productivity of capital is f dash k, and this has a diminishing f dash k, that is f double dash k, that is the second derivative of the function f is negative. So this is how, this is a assumption. So this has to be satisfied by the production function. Now growth of labor input is exogenously determined, that is dl dt, and labor grows at a rate n. Technology is also, growth rate of technology is also exogenously given, and it grows at a rate g, that is 1 by e de dt g, and this is n. So we will remember this. The Solow model assumes that each year people save a fraction s of their income and consume a fraction 1 minus s. Therefore we can say that the total output is given by consumption plus saving, and consumption is and saving is a fraction of the income. So and the fraction is given by small s. So this equation would be important later. We also assume that capital stocks depreciates at a constant rate of delta per period. So change in capital stock between one period and the next depends on investment, which raises the capital stock, and depreciation, which wears out the capital stock. Therefore change in capital stock is investment minus depreciation. So k dot t, so what they represent by k dot t is, so k dot t is, if we write it in discrete time terms, that is kt minus kt minus 1, this will be given by investment at time t minus depreciation at time t, right. So they represent this by k dot t, and this will be given by investment at time t minus depreciation at time t. So this will be the change in capital stock. The higher the capital stock, the higher is the amount of depreciation. Basically if we write it in constant terms, this becomes dk dt, not in constant, in infinitesimal terms, it becomes dk dt is equal to it minus delta kt. So this equation will be important later. Now moving on to the second part, that is the steady state growth. Now we are going to discuss about the steady state growth path of the Solow growth model. Before doing this, let us do some maths. So we know that y is equal to c plus I, therefore, and y is equal to c plus I, basically output is equal to consumption plus investment, and we can write y is equal to 1 minus s into y plus I. Now from this we get that I is equal to sy, that is investment is equal to saving, right? Now we substitute y and put in our f of k and we get this. So we can draw the line as, so this would be our fk, and s, remember s is a fraction, and also always remember s is less than 1 and greater than 0. Therefore when we multiply something with s, becomes smaller, so this becomes s of f of k, right? Now let's look at our notes. So our notes tells us that yes, so this is the output fk, this is the investment fk, this is capital per worker, and this is output per worker. So this part is investment per worker and this part is consumption per worker. Consumption per worker. Now let's look at the dynamics of the model to find the steady state growth path. Now we have, let's do this. We have k is equal to k by L. Sorry, this has to be the smaller k, right? Therefore dk dt becomes, so we use UV rule, so it is basically a 1 by, so it becomes L into dk dt by L square minus k into dl dt by L square. So this becomes dk dt into 1 by L minus k by L into 1 by L dl dt. So we can write this as dk dt into 1 by L minus this becomes small k into, this is the growth rate of labor force, so this becomes n. So if we go back to this, so we see that LT by L, this is n. So and then then we substitute dk, then we substitute k dot t by this, basically, wait, this. So then we get this equation. So from this we get 1 minus delta kt, because we substitute k dot t by that. So 1 minus delta kt by lt minus kt by lt into n, basically. So we can substitute I by L as small I, that is investment per unit labor, k by L as small k as capital per unit labor, and we can write small k dot t as I minus delta k minus nk. So delta is depreciation, so it will become I minus delta plus nk, and this I can be replaced by s of fk. So this is the key equation of Solow growth model. Let us write the equation down. So the equation is k dot t equal to s of f of k minus delta plus n into k, I think, yeah, into k. So this is the main equation. The change in capital per unit labor is equal to s of fk minus delta plus nk. So this equation you have to remember for UGC NET exam, because whatever question comes you can mostly solve it from here regarding steady state growth path at least. This equation states that the rate of change of capital stock per unit labor is the difference between two terms. The first term is actual investment per unit of labor and the fraction of output that is invested. The second term is the break-even investment. This is the amount of investment that must be done to keep K at its existing level. There are two reasons that some investment is needed to keep K from falling. The first reason is that some amount of capital is depreciating, and the second reason is that the number of labor in the population is increasing by a term of n. Therefore, this break-even investment is the minimum investment needed to keep the capital per unit of labor at the same state it was in the previous time point. Now, what is a steady state level? A steady state is a situation in which the economy's output per worker, that is Y by L, small y, and consumption per worker, C by L, and capital stock per worker, that is capital K by L, are constant. So, at every time point Y, C and K remains constant. Therefore, we first now if K dot equal to 0, that is this term, if this is equal to 0, then we see that S of Fk is equal to delta plus Nk. That is, at every time point we are only investing the break even investment, and that K star for which K dot T is equal to 0 is called the steady state level of capital. So, what will be the formula of this? So, we will just put K dot, so we will put this will become 0, therefore, S F K star becomes equal to delta plus N K star, and the K solution of this equation becomes the steady state level of K, and we put that K star in Y is equal to F of K, and we get the steady state level of output. And when we put this into C is equal to 1 minus S into Y star, this gives us steady state level of consumption, and this does not change over time. Now, let us look at how it looks graphically. Therefore, you find this equation and make K dot T is equal to 0, and for the value of K that we have for K dot T is equal to 0 is the steady state level of capital. Now, this is the investment and this is the capital per worker. So, we have Y is equal to S of Fk, this is actual investment, and this is the break even investment. So, this point where actual investment equals break even investment is called the steady state level of capital. Now, the reason this is called steady state is because suppose it goes beyond K star and goes to K2. Therefore, at K2 our investment is higher than the actual investment necessary. So, as investment exceeds depreciation and population growth, capital stock shrinks because our actual investment at K2 is less than the break even investment. We can see that, and therefore, our capital stock shrinks until the actual investment becomes equal to the break even investment, and we no longer have a capital shrinking. Therefore, if we come somewhere here, we are faced with a force which brings us back to K star. If we are at K1 where actual investment is higher than break even investment, then our capital per unit worker will keep on increasing until we reach K star. Therefore, we see that there are forces which make us converge towards the steady state. This is particularly why it is called a steady state. Always remember that in steady state, capital per unit worker, output per unit worker would not change over time. It would stay constant, and also consumption per unit worker would stay same over time. Now this is the phase diagram of the model. We see that we have k dot in the y-axis and capital per worker k in the x-axis. So as we go on increasing from 0, we see that our capital per worker increases until we reach k star. After that, our capital per worker starts reducing because our k dot becomes negative. So the phase diagram above shows that the steady state, which is unique, is also stable. It will be reached in the long run, that is asymptotically. When k is less than steady state level k star, the rate of change in capital per worker is positive and the capital stock per worker in k increases to reach k star. But when it is more than k star, the rate of change in capital per worker is negative and the capital stock per worker decreases to reach k star. So if you're here, you will go this side. If you're here, you will go that side. Now, in steady state with population growth, capital per worker and output per worker are constant. Because the number of workers is growing at the rate n, total output and total capital must also be growing at the rate n. Yes, that must be right, because since our capital per worker and output per worker are constant, and suppose we have 10 workers and that increases to 12 workers, then our total output and total capital must also grow, right? Otherwise per worker capital and consumption will reduce. So therefore we have y is equal to, we have y dot equal to 0 and k dot equal to 0 in steady state. This part we already covered. Now differentiating k with respect to time, we get, again we have already done this, dk dt equal to 1 by L dk dt minus k by L square dl dt. Therefore we take k by L common here and we get 1 by k dk dt minus 1 by L dl dt. So we have, in steady state we have this term, the left hand side term becomes 0, and therefore we have 1 by capital K dk dt is equal to 1 by L dl dt, which is n. Therefore we see that capital also grows at the rate n. Capital per unit worker does not grow, that is 0. The rate of change of capital per unit worker is 0, but the rate of change of capital is not 0, that is equal to the rate of growth of population. Same thing we do, we differentiate y with respect to time, then take y by L common and this term becomes 0 and then this term equals the n. So we see that rate of change of output per unit of time is equal to the rate of growth of population. But remember, the rate of change of output per unit labor is 0 in the steady state, but the rate of change of output is not 0, that is equal to the increase in population, which is equal to n. Now we are going to talk about the golden rule level of capital accumulation. Now if we were to introduce households into the model, their welfare would depend mostly on consumption at time period t. Thus, if there is a benevolent policymaker, that person would choose the steady state with the highest level of consumption. Therefore, the steady state value of k that maximizes consumption is called the golden rule level of capital and is denoted by k star gold. Now let us see if we can derive this. So we know that income is equal to consumption plus investment, and this is income per capital, income per unit labor, consumption per unit labor, investment per unit labor. Therefore we can write this as C is equal to y minus I. Now we know that golden rule level of capital is one of those, is a steady state level of capital. Therefore in steady state we can write C equal to F k star minus N plus delta K star. Right? Now we have to find the value of K star that maximizes C. So according to first order principle of maximization, we do dC dK star and we equate this to 0. So to do this, therefore we get f dash K star minus n plus delta, since dk star equal to 1 is equal to 0. Therefore f dash K star gold, because the K star that satisfies this equation is the K star gold, n plus delta. Therefore this is the level of, therefore at this K star our consumption is maximized, and we call this K star the golden rule level of capital accumulation. Now we are going to talk about the fundamental determinants of long run living standard. So what happens if we increase the savings rate? Now initially let's assume the savings rate was S1 and we increase it to S2. Therefore an increase in savings rate S shifts the saving function upwards. At the initial steady state K1 star, we see that at this point now investment exceeds the break-even investment, therefore capital stock per unit labor will increase until it reaches K2 star, which would become the new steady state capital K2 star basically. What happens if we increase the population rate? If we increase the population rate, then this line, which is the break-even investment line and is given by n plus delta, will shift outwards, because now n has increased to n2. n1 is the initial growth rate of population, n2 is the increased growth rate of population. So as population increases, now at the old steady state of capital K1 star, we see that the break-even investment is higher than the required investment. Therefore capital stock per person would reduce until it comes back to K2 star. Therefore if the rate of growth of population increases, the capital per worker in the steady state reduces. You will find the link to the PPT in the description. Thank you.